Hello, welcome everyone to the next lecture of electronic devices. We are talking about applications of the inverting configuration, and today we are going to discuss the last application and then we will move to the non-inverting configuration. So the last application, in the last lecture we talked about how we can do the integration, a time integral of an input signal using the inverting configuration. Today we are going to talk about how we can do a time differentiation of the input signal using inverting configuration. Okay, so we are going to develop this differentiator. All right, so the circuit, it's an inverting configuration. So we're gonna have a ground here. So rather than having a capacitor in the feedback loop, now we have a capacitor connected to the series, in series to the input. As you can see, it's almost opposite to what we had for the integration. Your rather than capacitor and the resistor positions are switched. Now your resistor is in the feedback and capacitor is connected to the input. So here's a capacitor, the current IC of t, the current over here will be IR. And of course, you're gonna have we're gonna consider an ideal op amp, so you're gonna have a virtual ground at this point. All right, so let's solve this circuit again. Since it's a virtual ground, so our currents will be the same. I see virtual ground. So IC of t equals IR. Now IC of t, the current that will flow through the capacitor, will be equals to C dVi of t over dt. Now since the currents are equal, so let's apply the Kirchhoff's law at this feedback at the output. So it will be 0 equals IR R plus V naught of t. So our V naught of t equals minus IR of t into R. Now since both of these currents are equal, so I can replace this V naught of t minus IR of t with this. Right, so this is, you can say like this. So I'm gonna put this value over here. So minus RC into dVi of t into dt. Now you can see that from this equation that your output is time differentiation of the input signal Vi of t. So this is how we can use the inverting configuration to develop a differentiator circuit. Now let's quickly, we can find out the magnitude and the phase response as well. So I'm going to start with the transfer function now. Transfer function. Transfer function will be V naught of s over Vi of s equals minus Rs, right? So it's a feedback. R is n divided by Xc of s. We know that it's a simple R, and for the capacitance in the S domain is 1 over Sc, so it will be Sc. So if we will, and we can replace S with J of omega to find out V naught of J of omega over Vi J of omega equals minus J omega Rc. So here's the transfer function of this differentiator circuit. So we can easily find out the magnitude response of this. So the magnitude response will be V naught of J of omega over Vi of J of omega will be equals to omega CR. So this is the magnitude response. And then we can also find out the phase response, right, which is your tangent inverse minus B over A for the complex numbers, right? So you can easily find the phase response as well. So phase response is going to come out to be minus 90 degrees. So this is the phase response of this differentiator circuit. right? So as we can see that using the simple inverting configuration, by using the resistor in the feedback loop and capacitor with the input signal, we can easily do the time differentiation of the input signal over here. So this is our differentiator circuit. Here's a magnitude response, and now I am going to draw the Bode plot of the magnitude response. All right, so magnitude response is omega CR. Again, omega log scale, and this is 0. This is V naught VI in decibels. So what do we see over here is our magnitude response what equals to omega CR. At omega equals to 1 over CR, and this is this, when omega equals to 1 over CR, as we can see, when we will put omega equals to 1 over CR, our V naught over VI becomes 1, and 20 log of 1 will becomes 0. So that is why this intersection with the omega line will be the magnitude response over here is 0, and frequency is 1 over CR. Second important thing that we can see from here is as omega increases by a factor of 10, magnitude doubles. So which means that there is a plus 20 dB per decade increase in this magnitude response, or 6 dB per octave. So another thing, the third thing that you can see from this magnitude response is, since this magnitude response is increasing, right? So and this is kind of a linearly increasing, sorry. Okay. That for higher frequencies, this is omega scale. As you go higher in frequencies, the magnitude response becomes more and more. Right? So for higher frequencies, magnitude response will be higher. Sorry. All right. So what does so this thing has an implication, right? So at higher frequencies, the magnitude response will be higher. So this means that if there will be any sudden change in the shape of the input signal, or if the input signal has these high frequency components, then the magnitude response will be extremely higher, or the circuit will become overload or get saturated. Right? So any sharp changes in input signal, so sharp changes are usually associated with high frequencies. Differentiator magnifies this significantly. Differentiator magnifies this significantly. Right? So these high frequency changes could be because of EM interference. EM interference. So our differentiator causes noise magnification. Right? So high frequencies can be saturated. High frequencies can be the magnitude response for high frequencies. Magnitude response for high frequencies can be saturated. right? Okay, so this will result in stability problems. That's why differentiator, or this differentiator, is usually avoided. Okay. Right, so this is what we sorry, so this is what we have seen thus far, that this was our magnitude response, and as we can see, it's as it is increasing linearly, the magnitude response is becoming much higher with higher frequencies. So as frequencies will increase in the input signal, the magnitude response will increase. And now those high frequencies are certain changes in the shape or the EM interference. Those frequencies can cause the output signal to get saturated or the circuit to get overloaded. So that is why differentiators can cause this noise magnification, and due to the stability issues, they are generally avoided. So there is one thing that we can potentially do to avoid that, is to connect a small resistor, in series with a capacitor. So there's this thing that we can do to help with that to a certain extent. That in the circuit we can connect a small resistor in series over here with a capacitor to help solve this problem to a certain extent. But the value of the resistance needs to be smaller. Otherwise, the resistor will become dominated in the differentiator circuit as well. All right, so this is our simple differentiation. The last application that we want to talk about for the inverting configuration is this differentiator. We have a capacitor again in series is connected with the input, and we have a resistor in the feedback loop. We easily ended up finding out this equation in which we saw that this differentiator circuit is doing a time domain differentiation of our input signal Vi of t. So we ended up finding the transfer function and the magnitude and the phase response of this differentiator as well. All right, there is one example that we want to do before we wrap up this lecture. This is a short lecture today. And that example is the example of the integrator that we did actually last time. All right, so now assume that here is your input signal. This is your input. This is t. This is 1 millisecond. This is 1 volts. This is Vi of t. This is 0. You have a resistor 10 kilo ohms, and you have a capacitor 10 nanofarads. Right? And this is an integrator. This is an integrator circuit, and we are interested in finding what will be the output. Right? So in the last lecture, we talked about the integrator, and this was the configuration of the integrator. That we have a capacitor in the feedback, and resistor is connected with the input, and look at the output voltage over here. So this is the output voltage over here. So this was output voltage. Output voltage was minus Vc, the initial voltage due to the initial condition. And then this voltage value. So this is what we are going to use now. Another thing that is given in this example is that we can assume initial voltage to be 0. Assume initial capacitor voltage to be negligibly smaller and can be ignored. So if that is true, then V naught of t is going to be equals to minus 1 over RC, 0 to t, Vi of t into dt. So using this equation, we can find out the output of this input signal Vi of t. So as you can see, the input is sorry, as you can see, the input can be divided into two different parts. For t going from 0 to 1 millisecond, and t should be greater than 1 millisecond. So in these two conditions, we can find out the values of the output. Right? So our V naught of t can be equals to minus 1 over RC, 0 to t, 1 dt. Let's also find out the value of RC as well, or 1 over RC, all right? So 1 over RC equals 1 over, what is the value of resistance? 10 kilo into capacitance, 10 nano. Okay, since we want to find out all the values in the milliseconds, all right, so what do we have here is going to be 3, 4, 5, 10 to the 5, 10 to the 9, 1 over 10 to the minus 4. So this will be equals to 10 millisecond. So 1 over RC is 10 millisecond. All right. So this is the value of 1 over RC. I'm going to use that shortly. Okay, so we saw that our input can be divided into two different components, two different time divisions. When the t is in between 0 to 1 millisecond, and when t is greater than 1 millisecond. So this is when t was in between 0 and 1 millisecond. When this was true, our 0 to t will be equals to t. And this will become minus 10 t in between 0 to 1 millisecond. Similarly, our V naught of t would be equals to 1 RT, 0 to t, 0 dt. This will come out to be equals to minus 10. The value will become constant as t becomes greater than 1 millisecond. So these are the two components of the output that we can easily find out. And now we can easily draw our output signature as well. Our output signature is going to be so this is V naught of t, and this is t. So since you can see that this is minus 10 of t in between 0 and 1, so I can do 1 millisecond, and let's do this is a constant minus 10. It's going to go all the way over here, and then it will become constant minus 10. Right, okay. So this is the output of the integrated circuit. So this is how we can easily find out the output of the integrated circuit. So we started with this equation that we already know. We assume that the initial capacitor voltage, that VC, was equals to 0. And then looking at the input, we ended up finding out the output at two different time ranges in between 0 and 1 millisecond, when our input voltage was 1 volt, and beyond 1 millisecond it was 0. So we ended up finding two output voltages for both of them, and then we can easily draw that, plot that. So we ended up finding out this thing. All right, so this is the end of this example problem as well. This was a short lecture today, and this kind of marks the end of the applications of the inverting configurations that we are talking about. And starting next lecture, we're gonna start with the non-inverting configuration. So in this lecture, we discuss the differentiation, or how we can make a differentiator circuit using the inverting configuration. We talked about this noise magnification or this high frequency changes. This differentiator circuit amplifies that. We can solve this by connecting a small resistor. And then we did one of the examples as well. So this is the end of today's lecture, and in the next lecture we are going to move towards a different configuration of an op-amp known as a non-inverting configuration. So we will quickly do that analysis, and then we will move to the applications of the non-inverting configuration. All right, so with that, thank you so much. Wish you best rest of the day. Thank you. Bye-bye.